This presentation will describe the motivation, background, implementation, and results of my master's thesis entitled Exploring the Impact of Opinion Ambiguity and Network Structure on an Agent-Based Model of an In-Play Betting Exchange. The high-level motivation for this project can be illustrated by the two images on this slide. On the left, we see a Wall Street trader frantically trying to secure a deal on the trade pit floor, whilst on the right, a relaxed trader sits back on his office whilst an algorithm does the work for him. Such algorithms have the potential to not only generate vast sums of profit, but also save large amounts of time and effort. Given this fact and the similarities that have been noted between financial markets and betting exchanges, it seems like an obvious question to ask why more attention has not been paid at developing automated algorithms that operate on betting exchanges. Two major issues may have contributed to this, which is price and data requirements. The concept of synthetic data can help to combat both issues, however. Cliff has made the first attempt at creating a synthetic generator of an in-play betting exchange, introducing the Bristol Betting Exchange, or BBE, platform. This platform is implemented through three main features that combine to replicate the real-world processes associated with human bettors betting on a track race event as it is occurring. On this slide we can see an example 4-competitor 2,000 metre race, as well as a technique used to better display the rank order of each competitor at each time step. The 6 types of bettors are displayed on a continuum of intelligence based on their strategy. The concept of narrative economics in 2017 by Robert Shiller inspired Lomas and Cliff to integrate opinion dynamics, OD, the mathematical modelling of opinion formation and evolution, into a simulated financial exchange. Guzelight furthered this by integrating OD models into BBE, proposing that a bettor's opinion be modelled as a weighted sum of 3 channels of information during the race, as listed here. This thesis presents an extension of the OD platform introduced by Guzelight, focusing on the design, implementation, and exploration of 3 interaction features. First, ambiguity is introduced to the interactions between bettors in 2 ways. A recently introduced modified bounded confidence OD model that uses fuzzy logic for the determination of interaction weights is implemented. Additionally, we present a novel method that models opinions pre-interaction, designed to replicate the ambiguity that can recur with opinions when they are expressed through language. Secondly, a network structure is implemented into the population of bettors via the Watts-Strogatz method, designed to achieve the properties of so-called small world networks. We introduce a further novel method for selecting the participants of an interaction based on the structure of this network. Finally, group versions of the BC and fuzzy BC models are implemented. This slide shows the description of the implementation of the 2 opinion ambiguity features. The FBC equation is displayed, where it is notably identical to that of the original BC model introduced by Hegelman and Krauss in 2002. The key difference is that the interaction weights are determined by a fuzzy logic system. We also introduced the novel method for opinion modification pre-interaction, and this is based on opinion strength. The logic for this is that stronger opinions are likely to have less ambiguity when expressed, whereas neutral opinions may have more. Next is the network structure feature. The network is created by the Watts-Strogatz method. Each node in the network represents a bettor in the population, and each has a pre-specified number of initial connections to its immediate neighbours. Each initial connection is then considered in turn, being rewired to a random bettor in the network with probability p. This is repeated until all initial connections have been considered. Increasing values of p result in an increasing amount of initial connections being rewired, as shown in the diagram here, from p equals 0 where there are no changes to p equals 1 where every initial connection is altered. Once the network had been created, it remained to implement a means for the participants of an interaction to be selected based on this network. To achieve this, we introduce a novel method that selects bettors with given probabilities determined by their degree of connection to the bettor initiating the interaction. First degree connections are selected with the highest probability, and every degree connection lower than this selected with half the probability for every decreasing degree of connection. Direct connections will therefore have around an 8 times greater chance of being selected than 4th or more degree connections. The last objective was to be able to compare the higher level effects of pairwise and group interactions for the BC and FBC models. As designs were already in place for pairwise BC and group FBC models, it was only needed was a group BC and pairwise FBC model. But the original group BC model was implemented through the same exact equation as the group FBC model, just with a different determinant of interaction weights, so this was the equation used. All that was needed, therefore, was a pairwise FBC model. This was simply achieved by flipping the weights of the pairwise BC equation, as the weights are always appropriate on the other bettor through the fuzzy logic system. Before describing the results, it is useful to provide a brief example of the fuzzy logic system used in the FBC model. The left side displays a flowchart showing the general processes of a fuzzy logic system, where a series of fuzzy rules are applied to an input variable x in turn. Such fuzzy rules can be displayed here, on the right with the rules matched by colour. If we take an example opinion gap of 0.1, which can be seen around here, this is seen to apply to the small and quite small opinion gap rules. This in turn relates to the strong and quite strong interaction weight rules. Aggregating these two provides the fuzzy set displayed here in red, which when is used defuzzification with the centroid method produces an interaction weight of 0.71. Having implemented the features, 6 exploration and comparison objectives were set, as listed here. 2 separate population and race scenarios were used to explore the desired effects, with the first being used for the first 3 objectives and the second being used for the latter 3. In the first race scenario, which is displayed here, competitor 1 takes a very early lead and continues to increase this lead to win very easily. The strategy weight of the privileged bettors was set to 0, meaning they could only be impacted by their interactions with other bettors. The population was set to be of high intelligence, this enabling the effect of the first 3 feature objectives to be examined, for what extent the privileged bettors could learn from the high intelligence Linux bettor strategies that competitor 1 was easily winning. The first objective was the examination of the 5 different weight segmentations within the FBC model. 5 simulations were run for each weight segmentation. It is clear from these density plots that the 2 lowest weight segmentations, C and D, did not allow the opinion to evolve much, finishing with only just higher than neutral average local opinion. Higher weight segmentations A1, A and B allowed privileged bettors to finish with much higher than neutral local opinion despite a strategy weight of 0. Weight segmentation A1 finished with the highest average local opinion just, so is used throughout the rest of the results for the FBC model. Next, the FBC model utilising the A1 weight segmentation was compared with the BC and RA relative agreement OD models. 5 simulations were again run for each. It can be seen that the average evolution and opinions of the BC and FBC models are very similar. The FBC does finish higher by 0.05, although this is 0.05 lower than the RA model. However, given that the RA model was shown by Guzelite to result in greater degree of consensus than the BC model, it is not necessarily surprising that it achieved a higher value in a scenario where there was a clear winner from early in the race. The final exploration for the first race scenario was lever of opinion modification pre-interaction. This time 10 simulations were run for each. It can be seen that both low and medium modifications finish with essentially the same average local opinion as the simulation with no modification. A low degree modification, in fact, actually helps the average opinion to finish slightly higher than no modification. This is likely because the effect of modelling an opinion in this way can be beneficial in some situations and detrimental in others, as the method is random in assigning either a positive or negative modification around the exact opinion. It can also be seen that increasing levels of possible modification make it easier for opinions to diverge in the earlier stages of the race, as all bettors start from the same neutral opinion. This can be seen in the high modification's wider variation between 5 to 30 seconds in the race, and potentially explains why it finishes with a slightly lower average local opinion. In the second race scenario, it is a much closer race, but competitor 1 moves into the lead just over halfway through the race and manages to win. This race scenario is used for the exploration of network structure and group interaction features. The strategy weight here is set to 0.5, meaning the privileged bettors can utilise their internal simulations, and the population was of lower intelligence, meaning that an easier comparison of network structure where the high intelligence privileged bettors are clustered together can be explored. Here, the effect of the interaction selection method is explored in combination with the selection of only direct neighbours or any random bettor across the whole network. This is a combination of objectives 4 and 5. 6 scenarios are explored from bettors only initiating interactions with their direct neighbours through 4 ranges of using the across-network method, but with different rewiring probabilities in the Watts-Strogatz algorithm to a fully connected network. The results show that the impact of this follow perfect order of being able to respond to events in the race. Those who only interact with a direct neighbour are able to respond fastest to events as they are gaining cumulative information from each other's strategy. A rewiring probability of 0 perfectly retains the same neighbours to each privileged bettor as shown in diagram A, but as the across-network selection is used, they are slightly slower due to outside interactions with lower intelligence bettors. This effect continues for increasing values of rewiring probability, which gradually removes the initial clustering and brings the situation close to the slow-reacting, fully connected interaction selection. Finally, we compare the effects of pairwise and group models for the BC and FBC models. 5 simulations were ran for this. What can be seen is that for both models, a group version allows for a slightly quicker reaction to events in the race, or the difference is negligible for the FBC model. It is quite pronounced for the group BC and pairwise BC model though, and finishes with a higher local opinion. There are several limitations with the project completed here. Due to the attempted wide scope of introducing 3 separate new features, it has not been possible to explore them in greater depth, such as a greater number of simulations or wider range of race scenarios. Additionally, as all bettors start from the same initial neutral opinion in each race, it is not realistic, as it is likely that bettors would hold different opinions going into the race. 2 methods introduced for creating ambiguity and expressed opinion in selecting interaction participants have been based on intuition and have no research to back them up. There are many avenues for further work. For example, research, as just mentioned, to explore how these values should be determined. In the fuzzy logic system, there are many avenues that could be explored, such as different membership functions or different defuzzification methods. Additionally, fuzzy logic could be combined with other OD models such as RA and RD. Thank you for listening.